Hello and thank you all for joining us in today's webinar. In this session, we will cover electromagnetic propulsion and see how we can improve the efficiency of these applications through electromagnetic design. Let's take a look into the agenda of today's webinar. So we will explore the advantages and the main application of the electromagnetic propulsion. The design challenges posed by these applications will be covered, and despite these challenges, EMWorks offers cutting-edge solution for precise control and optimization of different applications of electromagnetic propulsion. Some case studies will be shown to highlight the capability of our proposed solution. Before ending this live session, I'll be happy to answer your question in the upcoming QA session. So electromagnetic propulsion is a method of propelling objects that harnesses the power of electric and magnetic fields to generate thrust or motion. By applying electromagnetic principles, forces are created to propel an object without relying on traditional mechanical propulsion systems. This innovative technology finds practical application in transportation systems, notably seen in high-speed trains and experimental propulsion systems for spacecraft. This notably electromagnetic propulsion offers several advantages over conventional methods, including higher efficiency, reduced friction, and quieter operation. As a promising and forward-looking concept, it has the potential to enhance and upgrade various industries by providing alternatives and more efficient means of propulsion for vehicles and spacecraft. So electromagnetic propulsion systems involve a comprehensive consideration of various key design elements. The core of the technology revolves around manipulating magnetic fields, which when combined with factors like eddy currents and EM losses play a critical role in achieving efficient propulsions. Engineers must precisely control electromagnetic forces while monitoring mechanical quantities such as speed and positions to ensure stable levitation and propulsion. Different variables like materials, air gap, deviation, current, and the speed are carefully optimized to enhance the system performance. Magnet configurations, including the innovative Hallback array method, are employed to maximize the magnetic flux and hence the forces. The combination of linear and rotary motions further enables a more efficient propulsion methods. The temperature management is essential to maintain superconducting states and ensure a system or optimal system performance. So power efficiency, safety and reliability, magnetic interference also are a key design issues that should be addressed by designers while working on electromagnetic propulsion applications. In order to solve and cover all of these design issues and other related challenges, we propose an electromagnetic simulation package. EMWorks provides a complete simulation solution that can help designers to study and solve different issues that can be posed by electromagnetic propulsion applications. Our solution offers a 2D and a 3D electromagnetic simulation software covering both magnetic and electric fields. EMS is our 3D electromagnetic simulation software, while EMWorks 2D is a two-dimensional tool for electromagnetic and multi-physics simulation. They both can help to compute different results, including magnetic fields, forces, EM losses, and so on. At the earliest stage of the design, 2D analysis is recommended because it increases the productivity, reduces the time to market, and improves efficiency of the final products. In addition to this, what makes our solution unique is being integrated inside SolidWorks and Autodesk Inventor, which are two powerful CAD tools for more user-friendly use of CAD geometry software. So multi-configuration features and other parametric options are allowed by SolidWorks and Autodesk Inventor, which can help to test and solve different design configuration within the same model. Switching from 2D geometry to 2D geometry is automated by EMWorks 2D, and going back and forth is seamless. So you can use the same model for 2D and 3D simulation using the same and unique geometry. No need to change or sweep between different models. So in addition to that, parametric studies can be performed to cover the different design scenarios and conditions, like computing the force versus air gap distances versus deviation, input currents, etc. We can use SolidWorks distances, angles, mates, sketch dimensions, and more as variables. So our solution allows also the motion coupling to calculate different quantities, so for both 2D and 3D simulation. So this coupling to SolidWorks motion offers a wide range of features and allows most or complicated and real-life situations. So it has many features, so it can be combined. We can combine both linear and rotary motions. Also, we can use multi-axis or multi-direction forces in this. So you can also use a spring, gravity as a feature, initial velocity, and more also inside your analysis. So this can ensure, altogether can ensure a most complete motion coupling solution. So where the electromagnetic propulsion can be like modeled in a perfect way. So to be able to solve electromagnetic launchers and coil gun application, a field coupled to circuit analysis is required. It allows to generate the current through charged capacitors or different components or any other complicated power system. So altogether, again, provided by our solution, can answer most of the design challenges or can overcome these design challenges and answer your questions. It will help engineers, designers, managers to improve productivity, efficiency of their products. So we'll see some case studies where we cover these design challenges and see how EMWorks can help you to solve these issues. So move. So our first example is an electromagnetic levitation system used in semi and high-speed maglev. It is composed mainly of F-type rail, guidance, and levitation magnets. The 3D geometry of the model is created using SolidWorks. It represents a planar symmetry, hence it's recommended in this case to start with the 2D simulation to save time and increase the number of iterations. So the levitation magnets are used to lift the train, and the side magnets are added to maintain the train in a specific position, a well-fixed position. Having a native 3D geometry doesn't mean that you should go all the way to extract the 2D model. It needs only a few steps to get a 2D geometry ready for your simulation using EMWorks 2D. So we use a 2D simplification feature to convert this 3D geometry to a 2D geometry or 2D model ready for the simulation. So in addition to making this conversion straightforward, this automatic feature saves your original model, so your 3D original model as well. So you can use the 2D, then you can go back to your 3D geometry for a final validation analysis. So these are some analysis. We performed a parametric sweep analysis where the air gap distance is varied. Also the lateral distance is varied. So the magnetic field results are computed and generated for each situation, each scenario. The field increases when the air gap becomes smaller, so you can see that the field becomes higher, so when the air gap is smaller. So our post-processing offers options like fringe, vector, streamlines, so for a better results checking and investigation. So they help you to understand your system and how it behaves and how you can improve it. So next is the results, is the force results. So we can see the suspension force versus current. So we did a parametric analysis for the current, so we varied the current and looked at the force at different air gap distances. So the force is higher when the air gap is smaller, and when also the current is higher as well. So we can see at the right figure that the levitation and guidance forces versus deviation decreases when the deviation increases. So when your deviation increases, the force decreases, especially the levitation force. So while the guidance force remains around same value. So now we are checking results versus different configuration. This means that we are testing our design, we are changing the shape, we are adding new components. So we tested 3 designs, and we can see that the third design offers the highest force. So where we applied some magnets and so on, so we found that the force is higher for this design. And this is one of the advantages of the electromagnetic simulation software. It enables you to test many iterations, many design scenarios, so your ideas can become true through simulation without going to the prototype, which is an expensive process. So another example, which is the electrodynamic levitation. So we have a wheel which is rotating above a conductive disk. So there will be eddy currents generated in the conductive plate, and these eddy currents will act against the wheel. So there will be some thrust and levitation force both together, and this scenario needs both linear and rotational motion. Also, we may need multi-axis force, so to see the force applied on the conductive or on the rotating wheel, so in different axes, the vertical and the horizontal force. So here we can see different field plots. We have 2 scenarios here, 2 cases. One of them is alternating magnet, so we use it just some alternating magnet in-out magnets, and the bottom figure to the right uses the hallback, and this hallback is used to maximize the field in the outer direction of the this wheel. So we can maximize the field that is going to the conductive plate, and which will increase our results later. So here we can see the rotation of the wheel above the plate. The results, these results shows the current density, the induced eddy currents on the conductive plate. So another 2D plot or cross-section plot is shown at the right graph. So this is animation of the eddy current density. This is actually 2D plot made by the 2D simulation software, and the left one is a 3D simulation results. So you can have both of them. You can study either with the 2D or the 3D, but the 3D is the most accurate because it involves all different situations and conditions. So can move. So here we can see different type of results. So we see the force, the lifting force versus time. So at different air gaps, this is the left graph shows the lift force versus time and at the different air gaps. So again, the force is maximum when the air gap is smaller. So at 5 millimeter we can observe maximum lifting force. The middle graph shows the thrust force versus time also. So we have a maximum force when the air gap is small, and the force reaches its steady state after 10 milliseconds. So as you can see, the steady state is achieved around between 10 and 20 milliseconds. So the right graph shows the eddy current losses. So this is the lamped power generated in the conductive plate. So again, it's maximum when the air gap is small. So another example of electromagnetic propulsion is electromagnetic launchers and coil guns. So we have 2 systems here. So an example of electromagnetic propulsion, which is the coil gun, is studied in this live session. So we can coil guns are one of the example. So is known also as ghost gun or electromagnetic launcher, is a type of firearm that uses electromagnetic coils to accelerate a projectile to high speeds. The principle behind a coil gun is based on the interaction between magnetic fields and electric currents. So when an electric current flows through a coil of a wire, it creates a magnetic field around the coil. By rapidly switching the direction, means a time varying field, of the current through the multiple coils or one coil, so it can be one or multiple coils, the magnetic field can be made to accelerate a projectile placed between the coils. So coil guns can be constructed with variety of designs, including single stage, multi-stage, and can be powered by batteries, capacitors, or other electrical sources. So the power supply must be able to deliver a large amount of current, a large amount of power in a short amount of time in order to generate the magnetic field, which will create eddy currents necessary to propel the projectile at the wished or at the expected speed. So in a simple coil gun system, the power source may be a capacitor bank, which is charged up to high voltage using a power supply. When the capacitor bank is fully charged, the stored energy can be rapidly discharged through the coils to generate a magnetic field that propels the projectile forward. Coil guns have potential application in fields such as transportation, where they could be used to accelerate vehicles without the need for combustion engines or fossil fuels. So however, they are currently primarily used in experimental, so it's still in application in labs. So let's see some further examples. So here we can see a typical example of a coil gun with a single stage. The middle graph shows an equivalent circuit. So the circuit contains a capacitor, a charged capacitor, some resistance, and the coil itself. So this simulation needs a circuit coupled or a field coupled to circuit simulation or analysis. You can use your current as input directly, but it makes more sense, it makes your results more accurate if you use a circuit or electromagnetic analysis coupled to circuit, where you model your circuit within your electromagnetic simulation. So the right graph shows the resultant current produced by this capacitor through this coil, and it's, as you can see, it's high amount of current within a very short period of time. So you can see it's less than 1 millisecond. There is 14 kilo amp. So here are some plots of the electric fields. The magnetic fields. We can see fringe plot of the magnetic flux. So we can see the animation of this projectile moving because of the Lorentz forces generated on it. We can see also some field lines plots and vector plots. These plots can help to investigate different quantities, can help to optimize, to increase the field that can reach the projectile, and hence it's gonna increase the efficiency of the system. So eddy currents, so the eddy currents generated in the projectile is shown here. So you can see that there is a large amount of induced eddy currents in this projectile in a very short period of time. So the force, the Lorentz force generated on the projectile versus time, is computed by the software. It shows that the peak value of the force is around or higher than 80 kilonewton in less than 0.3 milliseconds. It's very short period of time. The displacement of this coil reached like a displacement of 50 millimeter in less than maybe 10 milliseconds. So you can see that it's a fast application. The speed of the projectile is shown in this graph. It shows that this projectile has very high speed, the acceleration as well. So there is very high acceleration reached within very short or a limited period of time. So this high response or time response can be used or can be used in many applications like automotive or aircraft or spacecraft. So yeah, let's take a look at the software, at the solution inside its environment. So let's move to a live demonstration. Let me switch to SolidWorks. Here we go. So we are inside SolidWorks as explained. So our simulation package, our simulation solution is integrated, is embedded inside SolidWorks and Autodesk Converter. So let's take the example of SolidWorks. So as you can see, this is our 3D model. This is a coil gun with a single stage. There is only one coil here, and this is our aluminum conductive part. So this is EMS, so you can load, you can add your EMS to your SolidWorks environment by loading it from the add-ins, from SolidWorks add-ins. So let's have a look at the analysis. So let's try to create one study. So as you can see, we have 6 modules. We have 3 modules for magnetic field calculation, which are static or magnetostatic for static field calculation, AC and transient magnetic, 2 solvers, 2 modules for time domain and or frequency domain and time domain simulations. We have also 3 modules for electric field calculation, including electrostatic, electric conduction, DC conduction, and AC electric. So in addition to this, we have few multiphysics options like thermal, both steady state and transient thermal analysis. So you can couple your electromagnetic simulation to a thermal solver to compute the heat generated because of the electromagnetic losses. So also we have the linear static solver to compute deformation caused by both thermal stress and electromagnetic forces. The motion coupling, which uses SolidWorks motion, so you can couple your electromagnetic simulation to motion analysis, and the circuit coupling, so you can couple your simulation to a circuit schematic, so you can model your power system or you connect your device to some loads. So and let me get back here. So in addition to that, we have the parameterization, so you can parameterize your variables, so whether it's they are like geometrical or simulation variables, so you can parameterize both of them. So you can run your analysis versus like some geometrical dimensions, some simulation variables like current, voltage, and so on. So this is also feasible. So yeah, once you create your study, you will have this tree which contains the materials list, so you can apply your materials from the library that is that comes with the software. So you can see this is the library of the materials. You can modify on it, you can add your own materials as well. So after that, you define your coil, so whether it's a solid or wound coil. Also you can add a leads wire coil as well. So here I can show you the stranded coil. So we have the number of turns, we have the wire gauge, wire diameter, and the filling factor, so and the type of the excitation, so whether you are using a current or a voltage. So this is the current source, this is the current we apply to our coil. So as you can see, we imported this current from an external file. So you can generate this based on a circuit simulation inside or using transient coupler to circuit analysis. So yeah, once you finish your coil definition, you apply a force, so Lorentz force in this case, to compute the generated force. So the mesh, so we have both user defined mesh and the adaptation option. So let's see some of the results. So the tabular results contains force, torque, inductance, and so on. So it has many tabular and lumped quantities. Let's see the force. The main force is along y direction. So this is the force versus time. So you can pop up this plot. So this can be exported, so you can save this as Excel file and so on. So you can use it in other software or for other purposes. So the field plots, so the 3D plots includes like magnetic flux, magnetic field, applied current density, the current density generated, so it includes both the applied and the induced eddy currents, force densities, and other results. So you can plot the flags. So here you can use some other options. So yeah, let's switch some parameters from this. So this is a vector plot, so you can see the magnetic flux distribution, and you can change the position. So yeah, you can animate as well this one versus time, so you can see the motion of our moving part versus time, which is caused by the induced eddy currents on the plate. So yeah, so can be seen here. This is the cross-section view. Yeah, so let's maybe see also the induced eddy currents. So this is the induced eddy currents as well. So this is the applied eddy currents in the coil, and the top one is the induced eddy currents in our conductive component. So yeah, so the conclusions that you can use electromagnetic simulation software to optimize, to enhance your devices. So by modifying different input parameters, by modifying the geometry, by improving your design, so you can also get a better product, so without sacrificing too much time and also available resources. Because if you go to the prototype phase without doing any of this simulation process, it's gonna be expensive process, so because you will spend money and time doing prototyping. But you can do all of this like a virtual prototype. So simulation is something like a virtual prototyping process, so you can do a lot of analysis, a lot of design iterations without too much cost compared to the prototype, the real prototype process. Yeah, so let's wait for your questions. So let's move to the Q&A session. Thank you.